everybody. It's nice to see so many of you here for the fourth session. I know that the second and third sessions were pretty intense, but if you manage to stick through, it's very, very worthwhile. If you're going to be going into anything related to ZK Tech, that knowledge is going to go a long way to making understanding it easier. I'm going to talk about the session in a second, just before we get to that. Again, just general points. Got the course material. You should all know this by now. We can drop it in the chat if anybody is missing it. And now is really the best time to ask any more lingering questions. This session might end up being a lot shorter. This session is also going to be quite different in style. So Ki Chong's here with me on the stage, and he's going to kind of chime in, asking questions whenever we're going over stuff, to make it a bit more conversational and try and emphasize different perspectives. And so if you ask questions in the chat as well, we're going to be answering those. Then there's the intro to SNARK channel. We can ask async questions, and that's for the future. That channel's active in the PSE Discord, and you can use that whenever. It's not just tied to this course. Just gonna, before I go over the clarifications, I just want to talk about this session again. The part of the idea in this last session is almost like a continuation of the first session, in that the second and third session shouldn't be necessary to understand what's going on here, although we'll mention those things briefly. This is going to be much more of a kind of high-level description and discussion again. Okay, that's what I wanted to add. But before we get there, I just want to add some clarifications from the third lesson. And this is kind of just repeating some of the things there to try and reinforce that info. So most SNARKs work with elliptic curves. Generally speaking, if it's not post-quantum resistant, it uses elliptic curves. Elliptic curves are just generally kind of faster and provide abundant security, but not against quantum computers. Specifically, the D-log assumption, this discrete log problem where you're trying to take a curve point and figure out what number it was multiplied by. The fact that we assume that's hard, that allows us to hide values in elliptic curves. And that's sort of the crux of how we can embed elliptic curves into our protocols and our systems. The main example, or the best example for this, is your wallet, your crypto wallet. If you've got MetaMask or whatever else it is, your public address is a curve point. I mean, it's usually the x coordinate, because you've got the coordinates. It's usually the x coordinate of your of an elliptic curve point, and you made that because you multiplied the generator, just some curve point we all agreed that we'll use together, by your secret key, which is just a big number, but it's in a field. And then we spent a fair bit of time on polynomial commitment schemes, discussing how they work, how they allow us to take a polynomial, commit to it, and then evaluate that point. And the system allows us to prove that these equations came from the same polynomial we committed to. And that's very important in how our proof systems work. And that's also one of the kind of modular component of proof systems, that the polynomial commitment scheme can sort of be swapped out for different systems. Generally speaking, it's not a developer who will do this. This is a kind of a ZK, like real research expert who's making a new zero knowledge system. For developers and people who want to use the tech, generally speaking, you're just going to take a system that's been implemented by somebody else and make your own circuits there. So in this last session, lesson 4, part 3, because the online content, it's part 3. We're going to briefly look at how polynomial commitment schemes are used to do verifiable computation in Plon, and that's just going to be a very high-level description and a bit of a sketch. We're briefly going to touch on what a constraint count is, because this is a kind of a common topic of conversation. And we're going to look around at a few different proof systems, specifically Plon itself, Groth 16, Halo 2, and ZK SNARKs, and kind of say different things. Kichong, I cannot hear you. Yeah, I can't currently hear you. I don't know if anybody else can. If they can't, I'm sure somebody will say in the chat. So if you're having a technical issue, then no. Oops. Okay. Well, we'll continue. Hopefully he can figure that out. And again, just reiterating again, please ask as many questions as you want here. This is like for you guys.
Can you hear me now?
Now I can hear you, yeah.
Oh man, I've been talking this whole time and I just saw everybody's ignoring me.
Sorry, that's gotta feel bad, man.
Yeah. Okay, yeah, I was saying trying to say before, yeah, this is very much more of an open session, so feel free to ask questions. This is also, especially like beginner introductory type questions. Like I'm going to be asking a few of those, so feel comfortable ask that. And what I wanted to add in was like Arrow was saying, there you don't if you don't understand all the math behind it that he's going over, it's okay. I think it's actually more important just to like know it exists, and when you hear things like commitment schemes and elliptic curves and things like you've heard of it before, and if you wanted to dive in more you could, but it's okay to not understand all of it because I certainly don't. So I just wanted to add.
Yeah, absolutely. I mean, it's kind of how it goes. Maths is a language, and the same as learning like a human language, whether it's Spanish or German, whatever else. In the beginning, when you hear people speak, you just kind of hear sounds, and then the first step is learning to actually decipher separate words that people are saying, and then to understand those words. So here, you don't need to know that well what a group is, but in the beginning, it's kind of recognizing that a group is a thing and understanding that term, and bit by bit, you can build on that knowledge. And the questions you ask don't have to be related to exactly what I'm saying now. It can be anything from a past session or anything even kind of in general that we haven't touched upon. So we're going to spend a bit of time now sort of going over what we discussed in the first session. Here was this picture, and I think it's really helpful to kind of just, memorize this picture. These are really the rough steps of a proof system. And I'm just to give it a bit more focus, I'm gonna sketch, just like draw that out line by line so we can kind of focus on it. This is everything we've done so far. Okay, let's do SNARK fundamentals.
Yeah, we wanted to
For
emphasize this kind of graph because if you not the graph but the image, because if you understand the whole thing, you understand most of it at quite a high level.
exactly. Like really that picture encapsulates, I would say, the minimum knowledge that most people should have about zero knowledge technology. They don't need to go any deeper. Of course, if you do, you can do more with it. But this like high level picture is sufficient for most things. So it starts off with having a value idea about something that you think would be valuable, and usually it'll be a kind of, on such a long word, entrepreneur who will come up with a value idea. And that person doesn't have to be distinct from the ZK expert. They can also be an entrepreneur, but that's just kind of like an entrepreneurial task more.
Yeah. So
And we
some
take that
examples
value
would be
idea.
how some examples would be how how you could use privacy, like what you could add to privacy to make it more private, and the other thing is scaling. So what you can scale. So those have been most of the core ideas so far, but there are many others.
Yeah, those are kind of the main benefits of using this technology. And it's not that, generally speaking, the researcher who knows how to make the best zero knowledge snark, they don't necessarily know about the business world or the medical world and computational world and where it will find value. So then we go to our idealized circuit, which is kind of a sketch in more detail of like what kind of computation are we doing, and how does that solve this value idea. So there is a bit of a sort of backward arrow here. showing how the idealized circuit would actually solve this problem or contribute that value. And then comes in the ZK engineer to arithmetize this into a circuit. Right, remember that was this process.
This step is where
Mhm.
this step is where you would need to know the math, right? At this ZK engineer. Before that,
Yeah,
you wouldn't have to know, but this is where you kind of need to get more into the detail.
exactly. Like I've said before, this is where a lot of ZK engineers spend their time. They're making circuits, so this is kind of quite math heavy. So circuit, and then in here is where the witness is added, and this is sort of our zero knowledge. This is the thing that's kept hidden and private and secret.
So the witness is all the values the prover adds into the circuit. Is that right? And some of those are private, some of those can be public.
Exactly. So this is our that's our starting circuit. Then the witness is just the remaining wire values, and I now will try and make this a valid circuit. So, and now this will be 3 plus 1 will be 4. 4 times 2 is 8. And all the red values are part of the witness, and these will remain secret. But all the yellow values were known to everybody. And yeah, this is our filled-in circuit. And then from
If
there,
anybody has any questions so far, feel free to ask also, or raise your hand or put it in the chat.
here, well, not let's do make polynomials. We take this circuit, and from it we make our polynomials, and that's based off how the proof system works. The proof system will dictate how you make these polynomials. In actuality, like, you're not making polynomials. This is from this point onwards, the library you're using is doing all this for you, but this is kind of what's happening under the hood a little bit. So, Whispering Woods, how do we fit a polynomial into a group to then use it? What we do is we'll make our. Let me just go further below instead. We'll make our polynomial. Well, we'll actually make several polynomials, and maybe this one is 3 plus 7x plus 9x squared. In reality, these will be really long polynomials, and the numbers will not be small. They'll be huge numbers. If we evaluate this at like 2, for example, we get 3 plus 14 plus x squared 9 times 4, which is 3 plus 14 plus 36, which is 53. Oops, not 1. 53. And instead of using this as a number, we can instead kind of evaluate it with our elliptic curve. So we don't get out 53, we'll get out 53g, where g is on our elliptic curve. And then because of this, 53g itself, g, it's on our elliptic curve, but it's in a group, the elliptic curve group that we discussed in the past couple of sessions. So now we have 53g instead, which is also within that group, because if you remember, we mentioned that the groups are kind of self-contained. If you add things together in a group, you're still going to get something out in the group. So in this way, we kind of get group items, group objects from our polynomials. And sort of the purpose of that in terms of like using it per se is we want to look at the behavior of this group object to see if it behaves as we expect. Because if it does, it's going to imply to us that that the computation was valid, because the polynomials themselves represent this circuit. Would you like to explain towards the end the whole journey of a transaction, which SNARK to generating proof and getting verified by the SNARK, and taking of SNARK that uses some sort of subtable as well as Plonk 3 or something? So we can have a brief look at that. I think that would be better done towards the end, because that's more involved and technical, and so we can do that in the sort of spare time at the end, because this session itself in general should be a lot shorter. So if I forget, just remind me at the end. As our filled in circuit, we go to our polynomials, we make the polynomials, and then we commit. Oops, wrong color. Maintain our blue. We're gonna commit to these polynomials. And this was the system we spoke about yesterday, but sorry, last session. And that's actually kind of what's happening here. When we evaluate these polynomials somewhere, what we get out we'll call our commitment, because it sort of ties us into this polynomial, but it doesn't reveal our polynomial. And it's the polynomial commitment scheme that allows us to make use of this commitment. And then we say we query our polynomials is the next step. And previously I've been drawing this as coming from the commit step, because it happens afterwards. But it might make more sense to draw this from the make our polynomials, because we don't use the commitment in this step. It kind of we're at least claiming in the proof system what we're supposed to do is use those polynomials that we originally made. It's okay, friendly. If I've mentioned that we're checking to see if the polynomials behave correctly, and I know that's kind of very vague, but it's a little bit involved, so I'm just trying to leave it very high level. It is not circuit dependent. It is proof system dependent. These polynomials that we make, Plonk, the proof system we're primarily kind of talking about, Plonk says if we make polynomials in this certain way, then we should then we can predict how these polynomials relate to each other. And that's the behavior I'm actually talking about, is how these polynomials relate to each other. And based off that, we should be able to determine if the circuit is valid. If let me finish this kind of walkthrough of what we've already done, and I can add to that just a little bit. So we'll query our polynomials, and then what we get out is our proof, which is usually denoted as a pi symbol, proof pi. And all this stuff, this is the work of the prover. That's what the prover does. They're putting in their witness, and then they're making these polynomials, and they're committing to them, and they're querying them. And this process, it takes a bit of time. This is where computational power is used. Some of the trade-offs are, if touch on that a bit later, but if you want to do this on a phone, for example, the phone has to actually make the proof, and it takes computational work. A not insignificant amount is the amount, is what I should specify, because afterwards comes the prover, the verifier. And what the verifier will do, let's take green. The verifier will take in the proof, and they'll also take in the original circuit. Check. We can call it behavior, or use the verification method that the proof system tells us to use. Again, the verifier doesn't actually personally have to do anything complicated. They're just using the Plonk library, and the Plonk library has a function to verify whether something is valid or not. And if it is valid, we're happy, or the verifier is happy. And if it's not, they're not happy. So this is the verifier. Okay.
So
So again,
Errol,
Mhm.
if you were a developer, like what part of this, if you understood this whole like journey, what part of it could you just ignore?
Very good question. For most developers, this um, all this proof making, sorry, not proof making. Why does it keep changing my lines? Let me do highlight instead. All this polynomial making doesn't matter. In fact, yeah, the primary thing that developers should be focused on is how I've said a couple times before, is this arithmetization process, because most ZK engineers, they're given kind of a specification of an idealized circuit and they've got to turn that into code. That's what they spend most of their time on. And it's not a straightforward process to represent computation as within the limits of your proof system. Remember, we have addition and multiplication. We've got these addition and multiplication gates. And that's very different to normal programming. You know, there's no I8 or U8 or U32. Ideally, you shouldn't be using if conditions. Um, you can use for loops. It's kind of fine. The nature of programming and in zero knowledge circuits is quite different, and that's basically where all their time should be spent. That being said, you need to be able to debug a bit, right? A lot of programming is debugging and figuring out why your thing doesn't work. You might get proofs that don't pass, in which case you want to understand a little bit what possibly went wrong and maybe where the problem is. It's of course going to be somehow in the way you designed your circuit, because you can have security flaws. The primary being that, like, your code, the circuit you made, doesn't exactly represent the thing it's supposed to represent. So yeah, it's really this arithmetization aspect, and there is some maths related to that, um, or kind of analytical thinking, like giving this process, how do we represent that with field elements and additional multiplication. There are more gates, of course, like I've mentioned, but we're using the very basic form here to limit the scope. What are the things verify depend on here, and what makes verification take more time in SNARK? Stark.
I think we're gonna get to Starks kind of later on. Maybe we can revisit that.
Um, yeah. Because we're going to touch on Starks later, and we can touch on that there. But the verify doesn't really depend on anything. They just take in a proof and a circuit and check whether the proof is valid for that circuit. But of course, for verifiers, it's not just whether they're sad or happy, because if a proof checks out, then, like, so what? Why does it matter? You know, if you fill in a circuit correctly, why should I care? That goes back to the start of this whole process of, sorry, wrong direction. Go back to the value idea. What does the circuit, a valid computation, actually represent? And if it means that you are the account owner and you want to send somebody some money, then I'm a bit more interested, and then we can work with it. If more people have audio issues, please let us know and we can attempt something.
Bro, we're just restarting.
Yeah. Product builder has good idea on what end user place should be. Has good idea. Typically in product builders user story. I think in terms of, like, the much bigger picture, where SNARKs are just one of the tools you're using. If you want to build an app, you might need a website, you need finance people, business people, outreach, you'll need the design of the app, the idea. The SNARKs are only really like a small part of it. They might be, for many applications, they're key and possibly central, but they're still a kind of segment of that whole process. I guess it boils down to like, why are you using SNARKs, and in what way are they being used in your product? They're used to confirm that computation was done correctly, or to kind of scale, or to add some zero knowledge aspect. I think in most cases, like, I'm not sure I'm exactly answering the question here, Charlie, but for end users, that it shouldn't matter for end users what technology you're using. You might want to give them comfort, make them feel good that what you're doing it works well and it's secure and it's safe. But user experience wise, I don't think it should matter to them. Like, hopefully it should be very, very seamless and fluid experience for them. Kind of going from the user story to the circuit is, in the user story, the user wants to do this specific thing or have this feature in their have this feature, and then the question is like, is SNARK the right technology for this, and if so, what is the computation that's necessary? Sort of, I guess, what is the value idea of in the user story? Yeah. Oh, I did miss. Oh, sorry, I missed some questions.
The whole point of block.
I'm using an app called Nebo. You can also import yes, which is really nice. So this is off topic, but just quickly there. Adding 2 points in elliptic curve to get the third. What are the guarantees that a hacker will not trace the original points? Yeah. So you can't trace if you just add 2 points to get a third, you can't trace to get the original because it's like literally unsolvable. Given just that information, there are uh, if the field is size p, then there are basically p many solutions, and there's no way to distinguish between them. If this is a circle, because this is modular arithmetic, if you add this point to this point, you'll get out this point. Sorry, and this is just gonna be quick. But if you want to know what added to this point, you have an infinite number of solutions and no way to determine between them. Like, you could have this point and that point, or you could have this point and that point. It's just like there's no way to decide from all the possible solutions. So a hacker can't go backwards in that way. I guess the same as normal numbers. Like, if we do 5 plus 5 is 10, then how did we get 10? Well, it could be 5 plus 5, but it could also be 6 plus 4, or 7 plus 3, or 11 minus 1. In this way, there's no way to distinguish between the possible answers. But going back to kind of the high level, there's just this picture here of understanding this picture is what most conversation will be related to. When you become more of a specialist, like, you'll be talking more about, is our arithmetization, is it optimized? Is it as small as we can make it? And also, is it secure? Does it represent it sufficiently well? Again, you can have a security flaw where a hacker could maybe break it because you're not checking everything you're supposed to check. Okay. So
Can't see your screen at all. I don't know if it's just me.
yeah, I just got a notification that I dropped off the internet. Give me just a moment. Any more questions you have along the way, Kichong?
No, I think let's move on to the next section.
Okay. So I'm just reconnecting and then I can get back in there. Don't know whether I'll be still screen sharing though. Let's head back. Share screen. There we go. And it should be back. So here we wanted to. This is extracted fully from the online content, and it's putting a lot of these pieces together. So we want to go over it because it's quite dense. And this is in the context of the picture we just sort of drew halfway through. Once we make the polynomials, we can commit to them using our polynomial commitment scheme, right, as we said. And then we can make proofs. We make the proof by the term is opening commitments. What that means is we take the polynomial we committed to, and we make a new evaluation from it, and then we make an opening proof that the new evaluation came from the same polynomial we committed to. And the purpose of that is so that we kind of lock in the computation. Once we say we finished the computation, we want to make sure the prover can't change it again. Because of course, if they could, then they might be able to break the system. So that's called opening a commitment, and we query the polynomials to get their opening, or in part to get their openings. And a lot of this stuff is kept secret because of the D log assumption, the discrete log assumption. The discrete log is sort of everywhere in elliptic curve cryptography, but it's in some places more than others, because when you evaluate a polynomial, you're adding lots of points together. So it's already kind of mixed up and hard to break. But it is still embedded there because any single point we can't go backwards from. And that's like central to the security, which is exactly why quantum computers breaking it breaks the whole system, because it is fully central and tied to everything. And then we'll use the commitments in elliptic curve cryptography to check that they satisfy the expected relationship. And the way we check that they satisfy the relationship is the Schwartz-Zippel lemma, if you remember. What ends up happening is that the polynomials we'll kind of mix them together, and we should essentially have two polynomials that embed all the information from the computation. And if the computation has been filled in correctly, these polynomials should be the same size, and they should actually just be the same polynomial. So what we'll do is we'll evaluate both of them at a random point, and we'll compare and see if their evaluations are the same, which is exactly the Schwartz-Zippel lemma. Because if we evaluate them at a random point and their evaluations are the same and the polynomials are the same size, then with 99.99999% probability, the polynomials are the same. Sorry, if the evaluations are the same, then almost definitely the polynomials are the same, which should only happen if the computation was filled in correctly. You know, that can take a couple to go from sort of not too much mathematical background to understanding that would take several hours, and even then, like it's connecting all the different pieces together to fully understand why it's the case. It just takes a long time to get used to. But the like I was saying, the behavior we're expecting is that the polynomials will be the same size and that they'll be the same polynomial.
Is the fact that they're the same basically the only information that's revealed? Is that kind of why it's zero knowledge?
Yeah, yeah. I mean, that's what we're more kind of checking that they're the same, and if they are the same, then we're confirming that the computation was filled in correctly.
Okay.
And
And most
zero
and
test.
D-log is mostly about hardness and security, right? You said it's everywhere, so it just kind of like guarantees a lot of these secure properties, right?
Right.
Okay.
Exactly. So in STARKs, for example, they don't use the D-log assumption because they don't use elliptic curve cryptography, but they have some other kind of security assumption. So D-log is something that's often sort of forgotten about because it's just assumed to be true. It's just a working condition, but it is central to how these work. Can't remember what a zero test is. The term really rings a bell. But yeah, I can't fully remember that right now. And then just before the halfway point, in fact, so probably further than halfway point, we have constraint counts. And I think I might have mentioned this along the way a couple of times, but this is a topic of discussion because let's just define it quickly. That the constraint count is just the number of gates in your circuit. So in this little dummy circuit I drew here, this is a useless circuit, of course. Our real circuits will be a lot bigger, but the constraint count is the number of gates. In this case, 3. In general, it's probably in the millions. And this is important because the larger the constraint count, the longer it takes to make a proof. So depending on your scenario, if you have some medical data at your hospital and you want it processed and to get it back, and you want to make sure that it was processed correctly, you're probably not in a rush. It doesn't matter if it takes a while to process the data when you get it back, as long as it's correct. But if this might be a more user-focused application and it's supposed to run on their phones, and it's going to take 20 seconds or a minute or even 5 seconds to make a proof, kind of very bad, UI, really not ideal. So we want to minimize constraint count as far as possible without compromising security. So constraint count is pretty important.
Constraint count, like efficiency, prover time, that's all, like that's a big bottleneck, right? Like a lot of the ZK engineers and research focusing on this, and like new proof systems are kind of focused on this area also in some way, right?
Yeah, exactly. I mean, going back to this image again, sometimes you might have a great value idea, but the circuit might just have a constraint count that's too high, such that it makes it not solvable with at least like modern current SNARKs. If it's going to take billions of gates, it's probably like completely impossible. I can't remember because the time limit doesn't grow linearly. It's not like if the circuit is twice as big, it takes twice as long. The factor is a bit more than that because for most of them, it's not linear. It's super linear. N log n for elliptic curve cryptography generally. And then the last thing is that for a system like Plonk, there is actually, based on our setup, there is a maximum circuit size. If we want to go beyond that, we've got to like reset it up again, and it's just annoying. Yeah, so that's the kind of first half recap, going over a bunch of that stuff, and then the second half we're gonna look over the different proof systems, just very briefly, high level, and talk about some of the differences. Should we take a break here, Kichong, or should we just kind of get through the rest?
Does anybody have any questions? This is a beginner's course. It's supposed to be an introduction. So does anybody have like very basic questions? Like feel free to ask here. And we have time later on too, but I think we'll take some questions then move on. And if you need to take a break, you can, should we say at 50, like 7 minutes?
Yeah, that sounds good.
Um,
43.
this is just a very short introductory course, Jimmy. Just like the high level overview of everything. So for more advanced material, here the 0x Park course will be the best place to go next.
Yeah, we've got there's links to the end of the content to a few places. We tried not to overload you with 30 links, but there's a few there that can be very helpful. I don't think you need to pause the recording. I guess we can always just edit it out, but there might even be questions that are useful to have in the recording.
Yeah, I was thinking the same thing. Anybody in Web3 clubs have questions? It's okay to have like a beginner question. You You can also raise your hand if you want to speak.
Yeah. In terms of how we represent data in a circuit, if you want to. Hello. How do we get this into a circuit? If this A and B and C, A, B, and C are field elements. So I'm answering the question of how you get a string into a circuit, a field elements in, some field FP. Then yeah, it's not clear how you get a string in, and it takes more work. You can't do this just in a single gate or wire. Like if you want to use ASCII, for example, it was like the American Standard for Communication Information, whatever. But it's a 7-bit code that represents all the English language letters and full stop, brackets, things like that, and some other codes. Then if you want to do that, is a 7-bit code. Then what we want to do is we want to make, we'll call it either a sub-circuit or a gadget. It's kind of its own self-contained little circuit. I'm just going to call it ASCII with a box. And when we put in A, it should basically output A. It should output A. And it should also put out a 1. Oops. Found all my stuff. It should output 1, but only output 1 only if A is less than, well, A is between 0 and 2 to the 7 minus 1. Because then that means it's kind of within our 7-bit range. But this is not a single gate, it takes a bit more work. So you have to encode stuff, and that has a bit of a cost when encoding a string. And there's going to be a variety of ways to do this and more optimal ways. There might be more advanced gates that can kind of do it in one gate, but then you've got to add additional component to your proof system. So that part, takes some work. So Whispering Woods, when you're asking about bugs in the low-level proofs, are you asking about bugs in the circuit creation or in the zero-knowledge proof scheme implementation? For the ZK proof implementation, generally speaking, these are well made because there's like a lot of contributors, a lot of like good people who know what they're doing. It's and a lot of components are kind of the mathematical operations that have to be done. Basically, proof systems are like kind of combining various mathematical operations in weirdly complex ways, but the actual maths that has to be done in each component is usually, it's not easy, but it's been done loads and loads before, and it's well understood and it's implemented very well, so you can kind of copy it over. And then you've got to like make sure you integrate it well, integrate it together well, so there's not often errors there. Because if there is, and you can sort of break it, then like you really like it's hugely consequential because you can sort of break everything. So there's a lot of work making sure that there's no errors in the implementation.
Yeah, it kind of
And
answers also Shelley's question, right, about using different circuits. You're using the same things again.
right, yeah. So the circuits can be reused as much as you want. Like once you write a circuit, if this is the circuit that you made, and this is a boring 3-gate circuit, but it might be a circuit that is the transaction circuit, for example. Once it's made, you can reuse it and reuse it and reuse it as many times as you want. If you want to modify it, then it'll take some work, but you can reuse it. If you're lucky, you might even be able to reuse the circuit in a different proof system. It depends on if the arithmetization between the different proof systems meshes well together, or if it's the same arithmetization. Okay, we're at 10-2, so I think we can continue with the second half. I just put this slide here again so we can refer to it when we talk about some of these other proof systems. And we're going to go over these four: Groth 16, Plonk, Halo 2, and ZK SNARKs. This is just kind of an overview of some of the differences between them, and we're going to investigate those one by one. We'll start with Groth 16 because it's sort of one of the earliest ones. The 16 is because the paper came out in 2016, and Jens Groth is the person who wrote the paper. So that's where it gets its name from. And the fact that it came out so long ago, as far as zero knowledge goes, means that it's been used a lot. So a lot of circuits have been coded with it. For example, Macy, the voting system at the PSE, a project there, and I think Semaphore as well, and a bunch of other places have used Groth 16. So and that's not just because it was one of the earliest ones that could be used. There are some very good reasons to use Groth 16. Most importantly is that it makes the smallest proofs. If proof size is the thing you want to optimize for most, Groth 16 is what you want to use. So that's going to be important if you've got to store the proof online in like an expensive storage place, or if tons of people want access to it or verify it, then you might want to really optimize for this group size. Or if you're going to have loads of these proofs, maybe in a proof system it makes sense because a voting system. I mean, depending on the scale, you could have thousands, if not millions, of these proofs. One of the differences from Plonk is that it uses something called R1CS arithmetization, which is rank 1 constraint system, and you can't. It's like tough. It's a bit harder to draw out what circuits look like with R1CS arithmetization. This is one of the reasons we chose Plonk, because you have these nice addition and multiplication gates. But rank 1 constraint system, it's not. I wouldn't say it's like really hard to understand, but it's just a little bit less visual. One of the key drawbacks here is that if you remember what a trusted setup is we briefly discussed it last session, but some SNARKs you have to kind of prepare to make proofs. You got to do some setup in the beginning. In the case of Groth 16, you have to do this setup phase for every single circuit. So once you make a transaction circuit, you've got to do a setup. And then once you've done that setup, you can reuse that transaction circuit as many times as you want. But if you want another circuit, like a voting circuit or an EVM, theorem block verification circuit, there's got to have their own separate trusted setups. And as a reminder, the trusted setup, if that's compromised, that circuit is like unsafe to use. I mean, the data from that trusted setup. But it's the security is if 100 people take part, you only need one person to be honest, right? Yeah, it's this toxic waste we call it. People are supposed to kind of make this stuff together, and then everybody deletes their share. And if a single person deletes their share, nobody can recover what was there. But if everybody maintains their share and secretly talks to each other, and then they put their shares together, they can actually work out they know what the secret is, and they can use it. But these are done like online in a decentralized way. So if you or I just took part and we deleted it, then suddenly it's safe and secure. So those are some of the trade-offs of Groth 16. And then we do Plonk. So of course, most of what we've spoken about here is in reference to Plonk. The arithmetization, the addition and multiplication, is called Plonkish arithmetization. the polynomial commitment scheme, the way I've been describing it is, yeah, it's called KZG, like named after the authors of that. But it's a very straightforward commitment scheme where you just evaluate these polynomials. The opening proof that I mentioned is a bit more complicated, but yeah, all that stuff's related to that. But Plonk doesn't have a trusted setup per circuit. It has what we call a universal setup ceremony. So that once we do the setup ceremony once, you can make any circuit you want in Plonk and do stuff with it. There is one caveat that there is a max size of the circuit. If in the trusted setup we made 1 million values, then the largest Plonk circuit can have 1 million gates. If you want to go beyond that, you can't take the previous 1 million values and add 9 million or however many you want to add. You've actually just got to redo the whole thing with a sufficient number of values to be output. And yeah, like Aman is saying, Plonk and Groth 16 itself both use elliptic curve cryptography, so neither of them are quantum secure, or plausibly post-quantum secure. But because we have a universal setup as well, and we don't have to do it per circuit, we can put a lot more effort into making this single trusted setup ceremony as good as possible. You can run it over the course of a month or 3 months or however long, and try and encourage as many people as possible to take part, which is what many people have done. I think there's actually a PSA project, right, called Infinite Powers of Tau. This trusted setup ceremony is sometimes called the Powers of Tau ceremony because the values we make, they're sometimes called tau and tau squared and tau cubed. Is the name give it to it. And I think that's just one that's constantly updating to keep adding more security to it.
Yeah, that's right. It is called perpetual powers of tau.
Perpetual powers of tau, right. And then we have Halo 2. So Halo 2 is what we call actually a recursive proof system. I'm going to quickly sketch out what that means, but let's touch on the other points first. It uses the Plonkish arithmetization. So if you've written a circuit in Plonk, you can then kind of just insert that circuit into Halo 2 and already make use of it. But the things that are different in Halo 2 to Plonk is like committing to the polynomials, and then how do we query them, and then how do we verify in the polynomial commitment scheme. So a quick thing, recursive proof means that we're not just proving our current computation. Like if I'm the first person to make a proof, I will make a proof of my computation, and then when you, Kichong, the second person, he'll make his own proof of his computation, but at the same time, he will prove that mine is valid. And instead of having two proofs, well, we'll still have my proof, but his proof will sort of contain my proof within it. And in this way, you can make a chain. Let's just quickly sketch that out. So
yeah, you can make a proof of proofs, basically, right?
Exactly. Like this is C1, computation 1, and we get out pi, proof 1, and then we'll do computation 2, and we'll get out proof 2, pi 2. And what happens is Halo 2 will actually just combine these into a single kind of pi 1, 1.2. Now, if we want to do a third computation, computation 3, we'll get out the third proof, pi 3, and then we can just put these two proofs together the same as we did before. And we can call this pi 1.3 for proofs 1 to 3. And we can just keep adding in one at a time new computations to this, because this proof size, like pi 1 to 3, it's not any bigger than the original computation, proof. All these proofs are the same size. So if we want to do a fourth computation, we can do that and get out proof 4. And then we can just kind of squeeze it into here, squeeze them together, get proof 1 to 5. So now if we take this if we verify this, it doesn't just verify C4 in a sense, Pi4. It also verifies computation 3 and computation 2 and computation 1. So this way this is why it's called like a recursive proof or incrementally verifiable computation. Bit by bit, we're building up this whole chain, and we can be sure of everything that came before. A potential application of this is if you can do this for blockchain state verification, then you can make a proof about the entire blockchain history, or Bitcoin history, or Ethereum history, and in a single proof, be sure that everything you've received was valid without having to do all that computation.
Yeah, this is kind of what this EK project is about. Basically turning
Right.
everything, all the transactions that happened in a block into a single proof, which would be recursive, so it would contain many other proofs, but that single proof is all you need to verify everything that happened in that block. So it's very
Yeah.
practical application.
Yeah, it'll be like the current ETH state you sort of have, and then you'll have updates, updates or transactions. And you can kind of squeeze these in together to check that they were inserted correctly and that everything that came before was valid as well. So folding is, I can't remember if Halo 2 falls specifically within the definition of folding, but Nova and many other proof systems do folding. And this is, I can't say for certain, I can't remember right now whether Halo 2 itself specifically is folding here. But folding is this idea of taking two statements and turn them into one statement. But these two statements have to be kind of the same thing. They're both n-sized NP statements, and they're turned into two statements into one instance of the same statement. In some sense, what Halo 2 does is, in proof verification, it does like the easy bit of proof verification, and with the hard part, it keeps adding the hard parts together, even though the easy parts are done. But in Nova, the entire proof verification keeps getting folded together. So I think Halo 2 is not technically a folding scheme because it's kind of like a little bit off. In the online content, we talk about cycles of elliptic curves. That's needed. Well, that's what Halo 2 uses to help make it possible. But we thought it might be more useful to focus on the idea of recursive computation in this online talk. And then lastly, we have SNARKs. ZK SNARKs. So SNARKs satisfy all the properties of ZK SNARKs as well. But they specify, and they call it a SNARK rather than a SNARK, to add emphasis to the fact that there's no trusted setup ceremony. There's the T, it means transparent. So what they're talking about there is that they don't need any setup ceremony. So in this sense, there's no max circuit size limit in the way there is when you have a trusted setup ceremony, and it removes one of these kind of security assumptions. Most of us believe that the trusted setup ceremony itself is fully secure, and you can trust it if it's done in the right way. It's good. I mean, I think one of the first trusted setup ceremonies, I think for Zcash, which is one of like the OG privacy coins, I believe there might have been kind of 6 people that took part in the trusted setup ceremony. At that level, 6 people, I would say that's not safe. Like, it's not a good foundation. You should have some concerns there. But the modern ones will have hundreds or thousands of people taking part in a decentralized way. There's no kind of gatekeeping about who can take part, and that design is much better.
Yeah, how much was how many people participated in that KZG ceremony from the Ethereum one? I think it's few hundred thousand.
Oh, is it? Wow. I mean, I
I
can't.
don't I don't remember.
I can't.
It was one of the, it was a really big ceremony.
Yeah. When I was at Alio, they said they had a few thousand people take part in theirs, which was quite big at the time. And also Tornado Cash, I think, also had a few thousand people take part in theirs. Um, but again, if if there's hundreds or thousands of people taking part, you just need one person to be honest, and not even necessarily honest, but incompetent enough to to lose their share, accidentally delete it or whatever. It's kind of very unlikely that hundreds of people will take part, and not a single one of them will remove their part. In terms of the best Stark or most optimized one, I've worked with Starks less. But generally speaking, proof system, the most optimized will depend on your scenario. If you're trying to optimize for scaling or like what kind of computation you're going to be doing with it, there'll be a few trade-offs to make, and there isn't like one generic best for overall, although there'll be some decent choices. But it really is context dependent. AIR stands for algebraic intermediate representation. And similarly, Plonk uses addition and multiplication gates. Air has its own description,
Can you
and
go
yeah, it
back to
looks
the that table, Errol?
yeah,
It might make more
so,
sense there. Charlie,
yeah,
error is like the way basically Starks make circuits. So it's
yeah,
part of the
exactly.
consideration, right? If you're gonna choose Starks, you gotta like want to use error, or at least be willing to accept it.
I mean, that's a really good point because if you're a ZK engineer and you write circuits in Plonk, which is what I did, then the way you'd write a circuit in a Stark is quite different. If you want to represent the same computation in Plonk versus a Stark, it's done in very different ways, and you can be amazing at doing it in Plonk, but if you've not done it much in a Stark, then you might have a bit of a head start compared to others, but you're essentially starting from scratch in terms of optimal ways to represent different types of computation.
Does it when you use the different systems and arithmetization choices like the how would you describe the differences like when you switch from one to another? Is it like using a different kind of math?
Yeah.
You're just
It,
comfortable in certain situations and less practice in
yeah,
others.
exactly. I mean, I guess it's like using a different programming language.
Okay.
Like the syntax is different for one, and then the way the things you have to be careful of are quite different. So like Rust does a lot of checking, formal verification, which can be annoying, but it also helps make programs that will always run and that will probably be faster. It's kind of annoying context switching. It is sort of a different maths. But that being said, it's not like, teaching French versus making food. Like there's still, of course, a lot of similarities, but if you're in the flow in one, you constantly translate into the being in the flow state for the other. And I think there was one more thing to mention about Starks. Right. So generally speaking, if something is post-quantum secure, it's slower or its proof sizes will be larger. This is kind of the core reason why we're not all just using post-quantum secure systems. There's a trade-off for being secure against quantum computers, and that's that it's slower or uses up more data. So one particularly important thing there is that this applies a bit more to encryption rather than SNARKs, but if something is not quantum secure when it's encrypted, then in 30 years' time, if quantum computers become a thing, whoever has access to that data can kind of unencrypt it, or whether it's your secret key, they can unencrypt it. If you've used your kind of secret key to encrypt a message, they can unencrypt it in 30 years' time. So that's a bit of a consideration with Starks. Many consumer applications, if people are, look at that data 30 years from now, probably not going to matter. But of course, there are scenarios that you should be more careful. Okay, so that's essentially everything we wanted to go over. Now, the things I would say to think about and try and remember. Oh, I didn't actually change these. My bad. The things to remember here. Are maybe it didn't. Yeah. So the things to remember here are the differences between the kind of different system. This image is a great starting point of some of the key differences, and we've not even covered everything here. We spoke about, you've seen Plonkish arithmetization, but you've not seen R1CS or air arithmetization or what it actually looks like. First off, knowing that those are things is good to know, and then if it comes to it, you might be able to explore what those are. Knowing the advantages of the different systems is quite helpful as well. But in the core components, like we didn't mention what a quadratic arithmetic program is. To be honest, that's probably not going to be too relevant to devs, like something you really need to know about. But in the bottom right, hash functions and Merkle trees, those are things that you should really know a bit about, because those come up in various places. Like in representing the state, we're going to use Merkle trees and hash functions together. And then going back, remembering this kind of image and all the detail there, that's the core. I'd say that's the core to learn. Like the core kind of picture to memorize. And then that gives us. Mhm.
The proof systems, was there anything that you could think of that was kind of the main things that are missing from maybe that table about why you would choose each one? Because you've worked with a few of them. But I just kind of assume like the efficiency is a big one, right? Arithmetization, because that depends on the expert, your SNARK, your ZK engineer, like what they're comfortable with. But I just wonder if there's kind of anything else like why you would choose different ones. Because I think I saw in the chat about each system suits certain design desires from Whispering Woods. So I just kind of wonder what kind of designs would be suitable for different things.
Yeah, yeah, exactly. I mean, so the systems here, they're quite sort of vanilla in terms of, I'm saying they're quite basic, but Plonk, Halo 2, Plonky 2, Plonky 3, they give you a lot of variability in what gates are actually allowed. It's not just additional multiplication in Plonk. You can add in different types of gates. If you do, it might slow it down a bit, but you can optimize your setup to be like, we want these types of gates and we probably don't need these. So if we ever need to do them, you can emulate them using the actual gates. And that way you can specify the proof system to help you out more. So even within each system, there's usually some specifications that can be made. But in the min-max space, the kind of key things are the size of the proof. Does the size of the proof matter? And do you want to trade off for that? Does the prover time matter? And do you want to trade off for that? Does the verifier time matter? Because you could have like something that's a slower prover but a faster verifier, or a faster prover but a slower verifier. There's all these kind of different trade-offs, and it's really system dependent. On top of that, you've got like eco. Mhm.
What reason would you want to like a trade off like faster prover, slower verifier, and vice versa for that?
I mean, I guess for a faster prover, if you want this to run on somebody's phone, there's going to be much more limited computing power there, particularly if it's like not just like, modern iPhones, and if it's older phones as well. You might be willing to have a slower verifier there if you can have proofs be made a bit more quickly on their own devices.
Makes sense.
All that being said as well, the ZK space is still very and changing like a lot very quickly. Some of the things that came out recently, there's Plonky 3, which actually I haven't had a time to really look at yet, but I've heard people say that you got a lot of variability there in what it can do, and it's like very optimal in a variety of other ways. You've got I think it's a SC1, or I can't remember its specific name, but my understanding is that you can actually just write your normal Rust code, and it will take your Rust code and turn it into a circuit for you. And remember, I said that this arithmetization is what we spend a lot of our time on as okay, circuit engineers. So in a way, it's sort of taking away jobs, but it's not exactly, because you've still got to like make sure it's functioning correctly. And if it can translate generic Rust code, it's not going to be fully optimal. And like, for your specific use case and company, is it worthwhile to really do an as optimal circuit as possible? And that's just like today, those didn't exist a year ago. And a year from now, there'll be other things. So it's very hard to keep up with all of these.
So it's possible, like in 5 years or so, these systems will like some of these might not be used anymore.
Oh yeah, yeah, for sure. Bit by bit, they'll be phased out. Like Plonk itself, I can't even remember if Plonk itself is really used in many places. Like it's a lot of the ideas they're embedded in other things in Halo 2. But I'm not like, aside from when a company is like, let's use this tool, Plonk, and then they build circuits in it and they start using it, it's then very hard to change the wheels on the bus when it's going at 60 miles an hour. So lots of them that already had them chosen will continue to use them and might do an update and change later to something faster. But Plonk itself as well keeps getting updated with new ways to modify it that make it a bit faster in a variety of ways. The Rust circuit tool name I think is SC1. It's not C1. It's okay. It's from yeah, I thought it was SC1. I'm trying to remember the name of the company as well. I would recognize it, but I can't say it right now. I'll find that afterwards and drop it in the chat. Um, Going to some of the other questions. So Spartan, yeah, Spartan's funnily enough actually like an older system. Came out a while ago, but then they kind of found
Oh,
SP1.
is it
Sorry, not SP.
SP1?
Yeah,
Thank you.
from Succinct Labs is who it's from. Okay, maybe I mean from that brief description there, maybe I'm not saying what SP1 was correctly, but maybe that in a more like containered position. So Spartan actually came out a while ago, but then I I I, I read Lasso, and then I was gonna look at like the way they'd modified Spartan, but I think they made a bit of a change to Spartan and then used it in combination with Lasso and Jolt to achieve what they're calling the proof singularity. But
Oh,
mhm.
yeah, go ahead. I'll ask you after you finish your thought.
Yeah, I like each system takes a while. Like to even understand Spartan itself is probably at least a week's worth of time, if not a month, if it's your first time looking at it. And then you've got all the other things that it's supposed to combine with. So it takes a lot of time to go over each of them.
Yeah, part of why we wanted to do this was to give like one really generic overview, and then as the different systems come out, you could learn them also, but it's all different details and components and stuff. But what I wanted to ask was, how when you see something new, how do you judge if it's like bullshit or it's like actually promising? Because it just seems like there's so many things. So, like, what do you look for in like a potentially interesting system?
Yeah, I mean that's true. I mean there's the initial kind of social construct thing of like who made it, who's the company, and what are other experts in the area saying about it. And it's primarily a community effort. Like very few people have time. Each system is very complex, and very few people have time to go and investigate whether all the claims are true. And you might have some heuristics to be able to guess as to whether something's actually possible or whether it's just kind of marketing talk. But you primarily wait to hear from the experts who have a bit of time to check it out, and then even then it depends on its relevance. Like it might not be a tool you could use anyway because of your specifications, in which case it doesn't really matter that it exists, even though it will make waves for new projects. So it's best just to trust the experts online who will go and post about it on Twitter, their findings and their beliefs.
I see.
We should go over this last slide with the further exploration. I'll just briefly talk through each of the links here. These are in the online content. I mean, this is a shameless plug, but I wrote a kind of Halo 2 tutorial that's similarly on Gitbook. It shouldn't take too long to get through. If you're interested in Halo 2 and coding with it, there's a SNARK tutorial with, I think it's Alan Shipaniak. I can't pronounce his name correctly. And that's sort of, I think it was Python coding, but also looking at how SNARKs work. So that's a bit of under the hood understanding of SNARKs and figuring out how to use them. So that's also, if you're interested in coding in SNARKs, it could be a great place. ZK Mesh is something I would extremely recommend. It's a monthly newsletter, and it's got a bunch of research articles that were kind of popular in the past month. So like research papers, and then like more general articles, and then videos. So it's like separated by content type, and you can just kind of look at the titles and decide which ones you think might be worthwhile to look at. It's a really good way to keep up with the space. Then a bit more like detailed reading. There's Vitalik Buterin's blog posts are always great. He has somewhere the one that links here. He's talking about ZKVM and kind of the design thinking there. Is more of a that one's more like thinking about how SNARKs can be used in the blockchain space. And then there's a Plonk by hand, which is really nice to understand the inner workings of Plonk, where it kind of sketches out in these mini circuits I've been drawing with these kind of 3 gates. It sort of takes one of those and actually makes the polynomials and shows you what happens. That's probably more like, that might go deeper than most people want. It's kind of understanding how to make like code the proof system, for example.
When you see the Plonk by
There's
hand,
the
though, you can see how really complex it is in
Yeah,
practice. Like when you go from your 3 gates to what they do in the Plonk by hand, it's like you have to have computers to do these things.
yeah, yeah,
Very cool.
exactly. But
So
it's
much.
really nice to read.
Yeah.
There's the PSE Discord. Um, yeah, the PSE Discord. There's tons of channels in there and plenty very very active people, and it's all trying to be segmented for different projects and discussion topics. So that's also, of course, very good. Then for a more advanced course, there's 0x Park. They have a lot of content out there, and it's very worthwhile to look through.
Yeah, they have a lot of things. You can get very advanced studying Xerox parts.
Yeah. Okay, so I think that's all the kind of core stuff we wanted to go over. So well done for making it this far. Like these aren't straightforward topics, and to engage in conversations, this is some of the most basic knowledge you should try and have. But it never ends here, as I'm sure you're fully aware, and you've got to kind of keep going and going over this stuff and seeing it used in different places, seeing the different proof systems that are out there, seeing who's using them, seeing how they're all improving. It's kind of a never-ending battle, particularly when it changes so quickly. Like really, a year ago, the space looked very different, and it, yeah, it's you can't keep up with it all. You've got to be very selective with your time to decide what are you going to focus on. Like, is it just do you want to spend a month trying to implement a circuit because that's going to help you become a bit more of a ZK engineer? Do you want to be a bit more of an entrepreneur, but also have some ZK expertise? So you want to see how it's being used in different areas and how the different proof systems have different trade-offs. Do you want to be a researcher and just kind of follow in a more specific area about how certain types of things are done? Do be very conscious about how you commit your time, and maybe also tailor it to the kind of potential job you want to find. Yeah, so thank you
Yeah,
very much
thank
for being here.
you. Yeah, and yeah, I just want to reiterate, it depends on what you're looking for, what you're trying to do. Um, so there are different paths, different things to understand. Thank you,
Yeah,
Errol,
yeah,
for explaining all these things. Because I mean, it helps me a lot. I definitely enjoy this whole process. So it's nice to just kind of
yeah.
see where things fit together. I think that's very helpful to understand. At least understand what you don't know, which I find to be one of the hardest things starting out.
Yeah, yeah, agreed. It's been extremely nice. I mean, so Kijong and I wrote all the content together. Like that wasn't me, that was both of us together. So thank you to you as well, massively for that. Yeah, it's been extremely nice. Also point out Charlie's post there as a a community chat tomorrow for Macy. Macy is
Okay.
the voting, like a voting system project at the PSC. It's something I'm very interested in. I'm quite into politics, and I think the having a decentralized online safe secure voting system is phenomenally a phenomenally important tool. So yeah, I'm always like willing to shout out the Macy project. If you
Yeah,
have any
there's a
lingering
lot of
questions, we'll stick around.
yeah, there's many projects, different events in the PSC Discord. There's also a whole series, a more advanced math series by Matan. Um, that's also on the PSC YouTube. So there's many ways to get involved more.
Yeah, I mean, I think the Matan's course, I think even that's like at least 17 lectures, if not more. And even once you go through all of those, you'll have a pretty decent footing for all the maths involved. But it never ends. Like, you have researchers spending decades of their lives and they understand tons of it very, very deeply, but there's still huge parts that they don't understand that well. So it doesn't matter. Don't worry or feel bad if you don't understand that much of it yet. Like, it really does take a while, and nobody knows it all.
Great point.
Um,
Okay.
a project idea for getting hands-on. Use Bonky
I feel
3 using
better when he
Bonkish.
says that too, Sheila.
Um, yeah, I don't have any specific project ideas. I mean, maybe a good idea. I think Kichong, you share with me. There are a list of project ideas already, right?
Yeah, there's like Vandata, which is built on Semaphore. They've got like a
Yeah,
good list of
I can
projects.
drop
I
that in
mean,
the link.
yeah, if you're interested in like working on something, you could check out like kind of the PSC GitHub and see what things are there. Um, but yeah, there's just tons of work on all different levels, research levels, efficiency, circuit writing, and then basically turning these things into user applications. And I mean,
Yeah,
space on.
if you want to do something hands-on, it doesn't really matter what you do. I assume the purpose is just to get more experience using it. So all you really have to decide is that, like, I want to build this thing, and it's best to keep that scope very limited. Just make it a very basic object or function that you want to prove. Like, it could be a Sudoku or something even simpler, or something that you're more interested in personally. But you decide upon that, and then you just stick with it and you follow it through until it's done. Because it's really the process there where you'll be learning things. And if choosing the right circuit or thing to build is going to motivate you a lot better, that's kind of up to you to decide. Although, of course, looking online for more recommendations can be helpful. But just choose something really, really basic and simple and try and build that, because then that'll be a really good starting point. So that when you can go beyond to have a discussion or have an interview that talks about it, you'll be have a lot to say.
All right. I think we're going to close it there, unless anybody has any more questions. Yeah. All right. Thank you. Thanks, Errol. Thanks, everybody, for your attention and your precious time. Very appreciate it.
Thank you, Ki Chong. Catch you all later.